Okay, so today's video is going to be on waves and their properties. So the first question that we have is, well, what are they anyway? And then the second question is, do they need a medium? Do they need a material in order to travel through? And the answer to that question is, well, it depends. And the reason for that answer is it depends on what type of wave it is. The first type of wave we have is what we call a mechanical wave. Okay, and a mechanical wave actually requires a medium. So an example of these mechanical waves are sound. Sound is a type of mechanical wave. A water wave. You can't have water with wave in the water without the water. A wave on a string, like a guitar or violin. And there are others, you could say a wave in a baseball stadium or a soccer stadium that needs the people inside of it in order for it there to be a wave. The other type of wave is what we call an electromagnetic. And electromagnetic waves can travel through a vacuum. That is, it could travel through nothing. And an electromagnetic wave is a fancy way of saying light. And when a physicist talks about light, they're not just talking about the light that you could see, okay, the colors of the rainbow. They're also talking about all the colors you cannot see, like X-rays and microwaves and radio, both your AM and FM. So those are all types of light, all types of electromagnetic waves, and they can all travel through a vacuum. Well, so what do they look like? Well, we have a single pulse, which is essentially just if you have a string, okay, or a slinky coil, and you disturb it once, you have a little, it could be a bump, it could be a triangle, it could be a square that's sent, and it's moving with some speed in some direction. So it's got some velocity vector to it. If it's a continuous disturbance, then we have what we call a wave. And a wave would then look like a sine graph, where there's peaks, there's crests, and there's valleys. And it too would also have a direction. This wave can be moving to the right or it can be moving to the left. It can't be moving both. So when pulses propagate, how is the medium disturbed? Okay, so we have first we have what's referred to as a transverse wave. And a transverse wave, the medium moves perpendicular. So perpendicular to the direction of the pulses. So here's a transverse wave, and I have a point that has been highlighted over 4 instants of time. So this wave is obviously moving to the right, so its velocity vector is to the right. So the first instant of time, since there you have a little bit of a valley here first, it's going to fall down into that valley, then it's going to rise up the peak, and then finally come back down. So the direction of this motion is down, then back up. A longitudinal wave the medium vibrates, and it does it so it is parallel to the direction of the pulses. And a classic example of this is sound. Sound is a longitudinal wave, and if we kind of look at this picture here, we have areas where this slinky coil is compressed together. Those are known, you guessed it, as the areas of compression. And then we have areas where the slinky coils are spaced far apart. This is the rarefied or the rarefaction area of the wave. And basically all that means is that further apart or much space between, not a lot of space between. And that's our example of a longitudinal wave. So if we are talking about sound, then we have air molecules close together in one area, far apart in another area, and then back close together. So you can model this slinky coil for any type of longitudinal wave. So here we have a wave that's got some numbers with it, and we're going to define a couple different terms. So the first thing is the amplitude. So this is nothing different than what you learned in your math class. The amplitude is simply the distance from the peak to the equilibrium, what's known as the equilibrium line. Okay, those line in the center. So it's from peak to equilibrium line, or you can notice here it could also be from equilibrium line to the valley. Okay, it is the maximum height or depth of the wave. And for light, it's sensed as the brightness. So the brightness of the light. And for sound, it's sensed as the volume. Okay, it's tough to visualize this wave for light. Okay, it's, I think, even more challenging to conceptualize this for sound, but we'll do our best to do so. So in our example, if this is 0 centimeters, and that's 4 centimeters, our amplitude in this case is 4 centimeters. I'm going to try to keep this up as much as possible. The next one is what's referred to as the wavelength. Okay, this is the distance between successive crests or troughs, and it's essentially the length of one complete cycle. So if we take a look at this definition, the amplitude, the wavelength, oh, and by the way, the symbol is the lowercase lambda. Okay, so looks like that. From crest to crest, that would be one wavelength. From trough to trough, that would be one wavelength. Or the length of one cycle. So I could say, what is the distance from here to there? All right, so now in our example, we have 8 centimeters, right? So we have 8 centimeters, and that is the distance for not just one cycle, not just 2 cycles, but actually 2 1/4. Okay, so from point H to point X is a quarter of a wavelength. So what I have to do in order to figure out the distance for one cycle, I take the distance for all of the cycles, 8 centimeters, and divide it by how many waves, so in this case 2.25, 2 1/4 waves. And when I divide those two together, I get 3.55 centimeters. So that would be the distance for just one wave by its own. The next term is frequency. Frequency is given the lowercase f, and it is the rate at which the waves are produced. Okay? In other words, how often they are produced. Their unit is a cycle per second, okay, which, since cycles don't really have a unit, it's just a number, it's a count. This really is a 1/second. And a inverse of the second is defined as a hertz, okay, H-E-R-T-Z. And we use the symbol for hertz as Hz. And for sound waves, it's sensed as the pitch. So those of you that are involved with music, when you talk about the pitch of a sound, you're really talking about the frequency of the sound. And for light, it's sensed as the color. Red has a different frequency as blue, and that's how a physicist differentiates between red and blue. And for our example, we want to know how many cycles, okay, or how, for one cycle, how much time does it take? So notice that on the x-axis here we have time. So what I'm going to do is I'm going to look at one full cycle, so essentially from the start to point C is one cycle, and that occurs at about 2 milliseconds. Notice the multiplier here, milli. So look at the unit, cycles per second. We have one cycle and 2 milliseconds. And since milli is the multiplier of 2 times 10 to the minus 3, this came out to be 500 inverses of the second, which is 500 hertz. The next term we're going to define is period. Period is given the symbol capital T. We've already talked about this when dealing with the pendulum, and it's the time to complete one cycle. Okay, the relationship between frequency and period, if you notice this is the time at which to complete one cycle. This is how often, how much time, how many waves you can produce in a certain amount of time. Okay, so they, by definition, they are the inverses of each other. And so since they are the inverses of each other, we can actually write it either way. Typically, however, it is defined as 1 over t. And so in our example, essentially, rather than taking 500 hertz, we do 1 divided by 500 hertz. And so that gets us a 2 times 10 to the minus 3. And notice that if you take hertz is the inverse of a second, so if you do 1 over 1 second, if you invert something twice, you're back to what you started with. Velocity is our next term. Okay, so this is just simply how fast the wave propagates forward or backward. And so if we think of our definition of velocity, especially average velocity, it is a displacement over time. Well, our distance here we're talking about is wavelength, and our time we are talking about is period. But since period is equal to the inverse of the frequency, I can replace the 1 over frequency in for wavelength, and since period is in the denominator, we ended up getting wavelength times frequency. And this is the most important relationship that we're going to be talking about during this unit. So in our example, it had a wavelength of 3.55 seconds, or sorry, meters wavelength, and then it had a frequency of 500 hertz. And if you multiply these, oh, and by the way, this is centimeters, and if you multiply these two together, you get 1775, and that is centimeters per second. Or you can write this in meters per second, and you get 17.75 meters per second. Okay, so either one. And then the last one we have here is talking about phase. So I know this is on the same side of your paper. So phase. Okay, it's the synchronicity of different parts of the wave. Okay, so we say they're completely in phase if they're the same part of the cycle, which I'll explain in a second, or they're completely out of phase if they're opposite parts of the cycle. So if we want to kind of list off examples, and I'm going to go back to the previous slide because I have the picture here. So if I want to find 2 points of the wave that are in phase, okay, so I'm talking about in phase, I can look at D and H. They're both on the top of the wave, okay, and they're actually 2 full cycles. So D and H are in phase. A and E are in phase. Now you might say, why not C? It looks like it's at the same spot, because if this wave were moving to the right, then the point A, the next instant of time, it's going to be going up the crest. The next instant of time for C, it's going to be going down the crest. So they're not actually moving opposite directions. B and F, notice that they're both on the troughs of the wave, the valleys of the wave. So they're at the same spot. So these are all in phase. And there's much more here. You can keep on listing. The ones that are out of phase, they're on opposite parts. So D is on the crest, F is on the trough. So D and F are out of phase. Now notice I mentioned A and C. A and C are on opposite sides. So they too are out of phase. And so I'd like you to come up with one more before you come in tomorrow. All right? So that's all for now. So these are some properties of waves. I thank you for your attention.